Welcome back to Geometry Class. I'm glad you're here because we need to be careful about the COVID virus. I'm sure that it's not out here or out there. I don't think it is. Alright, we're going to teach a class like this because we're really concerned about the coronavirus. So, today it's lesson 71. Back this thing up a little bit. We're going to teach lesson 71 and 72. So we're talking about translations, and here I can read it. It's translations, lesson 71. So open your book. To the page. I can't really read it. But anyway, it's lesson 71. You get the idea. So, glad everyone is here. This morning we're going to teach a class. But I'm really struggling underneath all this PPE. I think I need to remove some of it. I don't want to because I might get sick. I guess I will though. Carefully. Carefully. Anybody out there? I'm sure nobody out there. I gotta stay 6 feet away, so take this off. And I guess I would just take some of this off so I can teach the class. Well, yeah. Guess I'll take these gloves off too. I don't want to do that, but I will. Maybe just take one off. Take one pre-filter off. And hopefully you can start to hear me a little better. I can feel a little bit better. Or I can see better and stuff. So I think I might go ahead and take the respirator off while we're doing it. Oh yes. Now I can breathe a little bit. And I can begin to see a little bit better. But while we're doing it, we might as well take it all off and just be done with it. This is very useful if y'all need to borrow this thing. It's got a filter pack back there, and that way you can do what you need to do. Uh-oh. All right. I guess I'll take these off too. I don't know that there's much problem with getting the COVID-19 disease here. Anyway, hope everyone's doing well. We will begin again, since you probably couldn't hear me the best, we'll begin again with lesson 71. Geometry. I do not have your tests yet. As I'm making this video, I'm not in physical possession of your tests. As soon as I am, I will attempt to score them and grade them at my earliest convenience, that is. So stay tuned for that. All right, lesson 71, page 472. We're going to look at translations. I don't know how much of this you caught earlier. Talking about translations, and not translations of the Bible or translations of other books or whatever, but different type of translations. A translation, and this is a type of transformation. We referenced transformations earlier, geometric transformations, and this is a type of transformation. And a translation shifts every point of a figure the same distance in the same direction. A figure that is transformed by a translation remains congruent to its preimage. Its side lengths, angle measures, and other properties remain the same. Translations change nothing but the location of the figure. Important point. So we have a triangle A, B, C, and we decide we want to transform this triangle by performing a translation. That is, we're going to translate this, we're going to move it. And remember, we had talked about vectors. We could say, let's apply a vector, a 45-degree vector. And remember, vectors are starting here on the right and going this way. Counterclockwise is kind of how the measure. So 45 degrees would be 45 degrees from the horizontal. So in a 45-degree direction, and the vector has a magnitude of 10 inches, or 20 inches, let's say. So 20 inches. That means everything here is going to move 45 degrees this way, 20 inches. So we get a new figure up here somewhere. Like this, again, it would say A prime, B prime, and C prime. And because of my limitations, I drew it bigger, but it should not be bigger. It's simply the same triangle slid, if you will, slid this direction. Translation. Translation changes nothing but the location of the figure. And then that blue box, a translation is an isometry, meaning that the pre-image and its translated image are the same shape and size. Same shape, same size. Bad drawing, but that is a translation. All right. Example 1, a square has vertices as listed. And it says find the coordinates of the vertices of the image of square ABCD after a translation of 5 units to the right. Show the pre-image and the image on the same coordinate grid. So you probably need graph paper for this lesson. You may, and hopefully you have some. If not, ask Mr. Troy. We have it here in our classroom, our virtual classroom. Right here's the whole pack of it, 80 sheets, and it's here on the table. So ask Mr. Troy for some if you need it. All right, top of the next page, 473 is an important thing here to pick up. Mapping notation is used to indicate the way in which a point or several points should be transformed. So it's kind of like a formula for mapping, for translating. An example is, this is kind of the general form of mapping notation as they give it. Big T, the translation or the transformation of point X and Y becomes, and then whatever you do to it. So for example 1 that we did, not the first example of the triangle, but the example of the square in the book, example 1 was moving it 4 units, 5 units to the right. So it would be X plus 5 and Y plus 0. You're just describing in X and Y terms what you did. So for that first example, we simply moved it 5 units to the right. So every X coordinate was 5 units greater than the first one in the new image compared to the pre-image was 5 units greater than the X value. The Y value didn't change because there was no up and down movement. So look at example 2. The vertices of a triangle XYZ are as given. Find the image of XYZ after the translation, and then they have the translation mapping. So T translation, I forgot a comma. Translation of X and Y becomes, and then that's the point, and then your formula, what it is. So really the most important thing of this whole thing is what's happening right here and what's happening right here. What change is happening to the X value, what change is happening to the Y value. That's really what it is. So all the rest of this stuff is just kind of the procedure or the format. So for example 2, it is a change X positive 5 and Y positive 4. So you add 5 to the X values and you add 4 to the Y values. It's very simple. That would result in a shift up this way, not quite a 45 because it's not 5 and 5, but it's 5 and 4. So everything goes over 5 and up 4 in this new one in the book, not this one, but the one in the book is X plus 5 and Y plus 4. So again, the change in the X is 5, the change in the Y is 4, positive 4, positive. That's supposed to be an arrowhead, by the way. Positive 5, positive 4. And then also, we talked about vectors, but the middle of the page there, a translation for a polygon can also be represented using a vector. Placing the initial point of the vector on each point of the pre-image will indicate the position of the point on the image. Now, it's kind of like you have this arrow and it's oriented a certain way, and you just take it like we did, but here are the points. And you take that vector each time and place it here. Okay, the new vector goes here, or the new point, and this one, and you keep the same orientation. The new one goes here, and the new one goes here, and here's your new square. Just shift it up that way. Everything happens with everything moves the same amount. And then turn the page. This is an easy lesson. Example 4 is simply what they call an application. Character in a new animated movie will move from the point 4, -5, first to a point 16 and 3, and then to a point 13 and -2. And find the vectors the animators will need to apply to the character. Now, this is pretty old school. This is not how they do it anymore. Computer animation is a little more automated than that. But you're simply taking a point that starts at 4 and 5, 4 and -5, and then it moves to 16 and 3, and then it moves to 13 and 2. And so you check those. What happened the first time? From 4 to 16, that's a change of 12. And then from -5 to +3 is a change of 8, and that's a positive change. So the first vector has a component form of 12 and 8. And then from the second one, going from 16 to 13 is -3 in the X, and going from 3 to -2 in the Y means a change of -5 in the X. So you just check the differences between those points and you get it. All right, that's lesson 71. Homework for lesson 71. You can write that down now. I guess lesson 71 homework is, let's move it. The main thing of this lesson 71 is what I just erased. That translation mapping really is kind of the only thing you need to remember. And again, I'll write it down here. The translation of point X and Y becomes x and something, plus or negative, x negative 2 and y positive 3, let's say. This change is what changes every x value over here. The new x value will be this minus 2. The new y value will be this, whatever this was originally, minus positive 3. So these are the two pieces of information that you really need in this whole thing. But this whole thing is called mapping notation. All right, let's review. Lesson 71 homework is 2, 3, 6, 7, 9, 10, 15, 16, 17, 19, 26, and 27. I guess you can see that. And we're going to go directly into lesson 72. So once you have that written down, flip the page to lesson 72. Now we're back on circles, tangents and circles. And we will begin. The tangent, remember, is a line that intersects a circle at exactly 1 point. So lesson 71 is disappearing. We know what a tangent line is. It is a line that touches a circle only at 1 point. So something like that. Here's the point of tangency. If this is circle C, that's point C. So circle C, and then this is point A and point B. So line AB is tangent to circle C at point A. And we talked about how that there's different things. This is a right angle. If you draw a radius from the center of the circle to the point of tangency, it'll always meet that tangent line at a 90-degree angle. So this is some more. The point of intersection is called the point of tangency. We did that. A common tangent is a tangent to two circles. So we could have another circle over here. We could have drawn a smaller circle, and this is point B. So line AB is a common tangent to circle C and circle D. Common tangent. It's a tangent to both lines. Common tangents can be internal tangents or external tangents. And we'll talk about that more later. And recall from lesson 58, if two tangent segments are drawn to a circle from the same exterior point, then they are congruent. So we'll go over here, we have a circle and we have an exterior point here and two common tangents. So we draw one on this side of the circle and one on this side of the circle, and I missed. So we'll put the point up here. From the same common point, just this line drawn this way, and keeps going this one drawn this way. These segments from here to here is congruent to from here to here. So we could label them all and say it, but two tangents drawn from the same exterior point to the circle are always congruent. Now, solving problems with common tangents, they try to make it a little more complicated. Example 1. Given that line MR and line PN are internal common tangents to circle A and B, find the length of MQ. Well, point Q there has two lines drawn to circle A, and they give you 2x negative 10 on top and x positive 2 on the bottom. So those are congruent to each other, and you can set that into an equation, if you will. Or you can also use the circle B. QN they have labeled as x, and then QR is 12. Well, that tells you that x equals 12. And simply substitute that in there, so it's pretty simple. Thinking about external and internal tangents first. And just in general now, I want to give you a quiz. And the quiz is, if I have two circles, if I draw two circles up here, and they're different size circles, two different size circles, how many different ways can I draw them that will result in a different number of tangents? Now that seems it's hard to explain, but for instance, if I draw a circle here, and I draw a circle here, just touching this one, the smaller one it is, right there, how many common tangents can I draw in this drawing? How many common tangents are there? Well, of course, I can put one on top here, so I can hit that one and hit that one. There's tangent and there's tangent. And then I can do the same for the bottom, tangent here and missed, but there, supposed to be there and there. And could I do another one? That's a common tangent. I could actually, since these two circles are just touching each other here, I could draw a line right through there. And technically, this line only touches this circle right here, this circle right here, and this circle right here. So that's a way to draw the circles and have three common tangents. Now, are there ways to draw it where there's only two common tangents, or one common tangent, or more than three? What do you think? Well, let's just experiment a little bit. If those two are touching each other, those two circles are touching each other, what happens if I spread them apart just a little bit? So a big circle, or oval, and a smaller circle. Again, I could do the same, start the same way I did. There's one, there's the other one. Now I can't draw one right through the middle that touches them both, but I could go like this, that touches it right here, and touches it right there, which is a different point than this one. This one touches here, and here. This one touches here, and up here somewhere. This one touches here, and here. So there's three. Of course, I could go this way. You hopefully can see. That will be touching there somewhere, and there. So it's touching there and there. So that's a way that there's 4 common tangents. 4 common tangents this way, 3 common tangents this way. Are there any other choices? And the correct answer is yes. We could go, can you see down here? I think you can. We were further apart here, that equals 4. We were touching here, that equals 3. What happens if we start to move the 2 circles inside each other, like this? Well, I can do this one, and I can do this one. One there, and there, and one there, and there. Which to me is the only way to do it. Because if I go this way, in through here, that's not a tangent anymore because I'm inside the circle. Remember, tangents are always outside. They only touch the circle at one point, and these circles, these lines would touch it here and here as it goes back out. So those are chords. That's not a tangent. So this way is only two common tangents. Well, can we make it to where there's only 1 common tangent? And hopefully you can see it if you look at the pattern. These 2 circles are out here, and then they touch each other. That's 1 less, that's 3. And then they start to move inside of each other. That's 2. Now, you would probably say, well, put this little circle all the way inside the big circle. Then what happens? Okay, let's try that. Big circle and a little circle. Are there any lines that I can draw on that are common tangents to both? And the answer is no. Since this one is all the way inside, as soon as I draw a line out here, I can't get inside there. And if I get inside, then it's not a tangent anymore. So this one will give us 0. So we have 4, 3, 2, and 0. Well, I'd like to get 1. Is there a way to get 1? And maybe some of you are saying, yes, hope so. We were here, partly overlapping, and then we went all the way inside. What if we just move in slower and stop at a certain point? And that certain point would be like this, where these 2 circles are just touching each other that way. Then I can draw 1 line, and it is touching tangent to the big circle and tangent to the little circle right there, because the 2 circles are in a way tangent to each other. So there's our 1. So 1 or 0, 1, 2, 3, 4. You can have 0 common tangents, you can have 1 common tangent, 2 common tangents, 3, or 4. 4 is the maximum. In 2 circles, you can have from 0 to 4 common tangents depending how you orient them. That's just a way to think about common tangents. Turn the page, 478. Tangent circles are coplanar circles that intersect at exactly 1 point. And we have that here, and we also have that here. These 2 circles intersect each other at 1 point, and these 2 circles intersect each other at 1 point. The only difference is these are interior tangent, and these are exteriorly tangent. It's hard to say. Internally tangent circles and externally. That sounds better. Internally tangent circles and externally tangent circles. The 2 there. Now some more problems, and this starts to get into pulleys and mechanics and things like that, which is interesting. Look at example 2. It's the middle of page 478. Solving problems with tangent circles. In the diagram, circle Q is tangent to circle M, and line NP is tangent to Q, so it's tangent to the big one. The radius of Q is 5, and the radius of M is 2. That is, circle Q is 5, the radius of circle Q, and the radius of circle M is 2. Find the area of this triangle, the triangle QNP, which is the bigger one there, to the nearest square centimeter. Is that possible? Well, it's kind of pulling a few things together, and maybe I'll just draw it up on the board so we can look at it up here. It first looks like, well, there's not enough information maybe, but there is, otherwise they wouldn't ask. They wouldn't ask you to find it, of course. Let's see if I can draw this. Circle Q and circle with an N, circle M. then point N out here. This line went straight across, point N, and then up here was point P, and connect this. Now, bad drawing already. I should move this, since this is a tangent, it's drawn to the tangent line, which is right there. I'll put a point P over here and draw this like that. So circle Q is tangent to circle M, and then we have the dimensions of radius of Q is 5 and the radius of M is 2. So we could put a measurement here and say this is 5 from here to here, that's the radius, and this is 2 right here. Should we put it out here? Radius, 5, radius, 2. Now the question is, what is the area of that triangle? Well, we know this is 5, so that means that this is 5. Let's just see what we have, see if we can get anything. So we're going to say this is 5 from here to here. And since this has a radius of 2, this is 2, and this is 2. So we have a 2 and a 2. That means this is 9. This whole thing is 9. And this one right here is 5. So we have a 5 and a 9. Does that help us? If we pull that out, we have a 9 and a 5. Well, it appears like it does not help us. Although if you remember back a couple lessons, this is tangent because it says so. NP is tangent to Q. So this line is tangent, and here's a line drawn this way. Remember, we just said earlier this morning, if you have this tangent here, you have a right angle. If you have a right angle, you can use Pythagorean theorem. A squared plus B squared equals C squared. So 25 plus x squared equals 81. Do your math and solve for x. And you should get a line, a length of this. Then you need to find the area still, which again is area of a triangle is 1/2 a base times height. And remember that the base and height need to be perpendicular to each other, so you would use this as the base, and then this new line that you found as a height. 1/2 of that, 1/2 of this times this is the area. And there's more. Example 3, mechanics. A car has a timing belt that consists of 2 pulleys and a belt as shown in the diagram. The belt runs around the 2 pulleys and is tangent to both of them. Of course it is, if it's a belt that's running on a pulley. The dotted segments JI and JK have been drawn into the diagram to assist in finding the distance. Well, since the lines meet at point J, then JH is congruent to JL, and if you look on the diagram, JI is congruent to JK. Therefore, IH is congruent to KL. IH is congruent to KL. And so you put those together into an equation and solve for x, and you get 1.5 feet, according to the book. All right, that's it. So internally tangent lines, externally tangent lines, and some about them. Lesson 72. Homework for lesson 72. Write it down here. 72 homework. Good timing. 72 homework is 5, 6, 7, 11, 14, 16, 17, 24, and that's not supposed to be there. 24 and 30. So please do lesson 72 and 71 and have them done before 9 o'clock Friday morning.